Perfect, thank you. All right. Welcome to the 7th lecture. I hope you all had a very nice and relaxed Easter break and that everybody stayed safe with the increasing number of cases that we have out there again. So before I start the lecture, an announcement, which I should have made a week ago, actually. So it turns out that in the course of this lecture, in this course, I will take 9 lectures. So there are a total of 14 lectures and expected to take 7 to 8 lectures at the beginning of the course and on discussion with Lídia in terms of the topics that I wanted to cover and that she would like to do. I will be doing 9 lectures. So this is the 7th lecture, and the next 2 weeks remaining in April will also be taken by me. And then Lídia takes the last 5 lectures for the quantum foundations topics that she will do. Right, so, and what we have left essentially in this lecture, we do autonomous thermal machines in as much detail as we can. And then the next lecture, I will talk about clocks, and the last lecture will be a little bit more about clocks, a little bit about coherence manipulation, or any other topics that I would have liked to cover in the course, but didn't get a chance to. And so that will be the 8th and 9th lecture. All right, so that brings us to autonomous thermal machines. So, so far, all of the thermodynamics that we've been doing is discrete, sort of repeated operations thermodynamics. And what this means is that we always had a setting in which we had some system and a state of the system, and then we would bring in other systems. So for example, we would bring in the thermal state of a bath, for instance, and then we would do some unitary operation on this. And of course, when you trace out the path, you get the final state of the system. And in different protocols, we had different such unitary operations, and sometimes we had repeated unitary operations. So for example, in the case of trying to erase a qubit, so if we had a qubit system, degenerate qubit system, the manner in which we could erase it was to keep swapping it with qubits from the bath of higher and higher energy gap until we got arbitrarily close to just being in the ground state. And if we did this repeated we would be closer to the reversible limit. So we would use up less energy in the case of doing many little increasing swaps rather than one big swap. But this picture, of course, requires a multitude of unitary operations to be done, and unitary operations themselves are not exactly free. We somehow based all of the thermodynamic paradigms that we considered on the concept of a free unitary operation. But when you think about how we would do a unitary operation, well, this is much more involved than just a free operation, because if we were given a unitary U to be performed on some system, the way we would go about doing it is we would say, well, let U be e to the minus I h int times t for some h int, which is a Hermitian operator, and for some t, which is a positive real number. And then we would implement h int on the system for t. So for example, from t, well, let's say, well, okay, let's call it c, from t is equal to 0 to t is equal to t, to be redundant notation. But this means that we have to switch on an interaction Hamiltonian, and then we have to switch it off, and we have to do this quite precisely, because if we do the interaction Hamiltonian for not the exact time t, then we will not get the unitary that we actually were aiming to get on the system. So how we will do this and how we will include a physical system to actually manage to do these unitary operations, we will discuss this more when we discuss in the next lecture, when we discuss clocks. But for now, all of this is to say, doing a unitary operation involves constructing an external interaction Hamiltonian, and then fine-tuning this Hamiltonian, switching it on and switching it off at particular times. And doing this over an entire protocol can actually lead to a circuit, if you like, a quantum circuit that is very complicated. So in the case of the protocol for erasure that we considered up here, if I have n qubits from the bath that I n gates like this, and each gate involves the construction of a completely different unitary operation because it's a different system and a different Hamiltonian that I need to turn on and off. So what we would like to do is we would like to consider whether there is a form of thermodynamics that we can do which does not require us to have such fine-tuned control. So something that has much less control. And we know that this is possible just from classical thermodynamics because you can just take, for example, a car engine. If I sit inside a car and I turn the key in the ignition and the engine turns on, it remains on as long as there is a fuel source that keeps providing it fuel. So somehow the engine is an autonomous machine in the sense that the working of the engine itself maintains the perpetuation of these cycles, the Carnot cycles that the piston in the engine goes through. So the engine provides work, and the work is also, some of that work is used to sustain the engine's motion. And in doing so, the engine runs indefinitely without any external intervention. Now, of course, eventually all such machines will wear out, but this is a different time scale that we are not interested in. We are only interested in the time scale once you construct the machine, and assuming the machine's components itself remain the way they're constructed, will it work indefinitely or not? And so what we want to do is to construct autonomous quantum thermal machines to replace all of the discrete thermodynamics that we've been doing so far. Okay, so the first example we will consider is a very simple one. It is that of a 2-qubit thermal machine. I say machine, that's a very strong word because it doesn't, thermodynamically, it doesn't do anything interesting, although quantum mechanically it does. And so here's the scenario. So I have 2 qubits of the same energy gap. So this energy gap is just E. And also in the setup are 2 thermal baths. This is at beta hot. And this is at beta cold. Okay, so my initial state is just going to be tau, let's call this qubit C and let's call this qubit H because they're going to be connected to the cold and the hot parts. I have that beta hot is less than beta cold, meaning that T hot is greater than T cold. So as you would expect from notation, the hot path is the H path is the hotter path. Okay, so my initial state is going to be the thermal state tau C tensor tau H. So just as a reminder, this is 1 upon 1 plus e to the minus beta cold E, the ground state, plus e to the minus beta cold E, 1 plus e to the minus beta cold E, the excited state of the C qubit. And this is similarly for the hot. So in other words, each qubit sort of starts in the thermal state corresponding to the temperature of the adjacent path. And now I do the following sort of scenario. In step 1, this is a cycle that I construct. I swap C and H. So this is I can write it in this form, this interaction. So the unitary that does this is, so it says takes 0, 1 to 1, 0 on CH, plus 1, 0, 0, 1 on CH, plus identity on the rest, which if I write it as a matrix is just going to be this 1, 1, and zeros everywhere else. Okay, right. So the result of this is going to be, so the result here is the states are switched because this is just the full swap. So the initial state of the cold qubit is now in the hot qubit. The initial state of the hot qubit is now in the cold qubit. And now in step 2, I thermalize each qubit to its bath temperature. So The cold qubit is thermalized to the cold temperature. The hot qubit is thermalized to the hot temperature, or rather the C qubit is thermalized and the H qubit is thermalized. Now, what is thermalization? I think we did this early in the course, but we can write this very simple map. So the thermalization map, which I can write as D, let's say with respect to some beta on rho, is basically equal to just tau at that beta. So you just take any state of the system and you replace it by the thermal state. So this for a single system is very easy to write, but for multiple, if you have a system that is a subsystem of a global state, then thermalization is more interesting. So imagine that we had systems A, B, C, D, ... and we only want to thermalize system C, for example. So we have D beta on C on a global state A, B, C, D, ... What you do is you take out the part of the state that corresponds to the Hilbert space of C. So that's trace over C of rho A, B, C, D, ... And you put in back the thermal state at beta of system C. So very simply speaking, I have a global system. I replace the reduced state of the particular part of the system that I'm thermalizing by the thermal state of the particular temperature that I'm thermalizing to. Okay, so there are two properties of this. So the properties, one is that, so the final state is product thermal on C. So what this means is that it's not just that I went from my initial state to a final state whose reduced state on C looks thermal. No, the actual final state looks like the thermal state on C, tensor product, everything else, which is a reduced state of what it was before. And the second thing is, what this implies is somehow a consequence of the first, is that all correlations of C with the rest are lost. So whatever correlations were built up in the state between C and the other components or the other subsystems are lost. One easy way to see how you could implement a thermal map is by a replace operation. So what you do is you simply physically take the system C, you throw it out, and you bring in a system from the bath that has the same Hamiltonian that C originally had, and you place that in the space that the system C was in before, and that would give you exactly this map. And by throwing out the other systems, the original system C, we've lost all of the correlations that C had with any of the other subsystems involved. Okay, so at the end of step one, what we get is, so we started with tau cold, tensor tau hot. What step one is going to do is it's going to take it to tau hot, tensor tau cold. So we're going to have, so a hotter qubit here, or well, a hot temperature here, next to the cold bath, a cold temperature here, next to the hot bath. And now my thermalization is going to be induced by some interaction with the bath. So we're not as yet discussing what interaction would make this thermalization map happen, but it is some interaction that induces this map, and we require it to be energy preserving. And this is not so much of a requirement as much as a consequence of physics. If you have a thermal bath and the whole thing is an isolated system, then whatever interaction causes the thermalization to happen is one that is energy preserving. So typically it happens via the exchange of energy between the bath and your system. So if it is energy preserving, it means that whatever the change in energy of the system is, I'm going to have the negative of that change in energy on the environment. So I can say that QC, and let's put it as QC in. So this is the heat into the cold bath is going to be equal to minus delta E of C. So, and now here with C, I mean the C qubit. So whatever the energy of the C qubit changes, it has to be matched by the heat that is put into or drawn out of the bath. Now, what is thermalization going to do? After step 1, we see that C has gone from a cold thermal state to a hotter thermal state, which means that its energy is going to be higher. It's going to have a higher population in the excited state than it did before. And via thermalization, it's going to return back to its original state. So its energy is going to decrease, which means that whatever energy decrease it has, that much of heat has been put into the cold bath. So QC is going to be greater than 0. And similarly, QH is going to be, is going to be less than 0, meaning heat will be drawn from the hot bath. Furthermore, because EC is equal to EH, that implies that delta EC is equal to minus delta EH, which also implies that QC is equal to minus QH, or QC plus QH is equal to 0. This is a consequence of the following two things. First of all, the swap 1001 plus the Hermitian conjugate is something which matches whatever population goes down on one qubit, that much has to go up on the other, and vice versa. And this, plus the fact that EC is equal to EH. So whatever population goes down on the first, the energy difference due to that is exactly the negative of the energy difference on the other, because the population change is the same, just in the opposite direction, and the energy gap is the same. This is the same as saying that the unitary that we chose, this unitary, commutes with HC plus HH. So it's an energy preserving interaction unitary, because it whatever energy decreases in one of the systems, it increases the energy in the other of that system. Okay. Are there any questions so far?
Yes, I have a question regarding the thermalization. Why this system C that we thermalize as a subsystem, why all correlations are lost? I thought about a simple system, say with 2 qubits, one at my place, one on the other side of the Earth, and they both are fully entangled. And now when I thermalize my qubit, isn't that a local operation which should preserve entangledness between the 2 qubits? Or
yes. So
yeah, where
indeed,
does this loss of correlation come into play?
Yes, that's a very good question. So so if you took the example that I gave of a replacement operation, where I take away this qubit and I put in a new qubit from the thermal bath, what's happening is that that correlation is now, it still exists in some form, but it's with that qubit that I've discarded. So when I say that the correlations between C and H are lost, it means between the system that is there, C, because what I've done is I've thrown away the state of the system, in the sense I've discarded that. Let's say imagine that was 2 particles, and I discarded one of these particles and I brought in a new particle from the bath, then the new particle would not be entangled with H. It would still be the old particle that was entangled with H. And when I say I discard the old particle, I say that what I imply is that there is no way in the future to make any operation that uses that entanglement that existed before. Another way of putting this is, and this is a more, I would say, physically meaningful sort of process, is you can imagine that C and H are, say, maximally entangled, and then C is interacting with its bath. As a result of C interacting with its bath, some of the entanglement between C and H now becomes entanglement between the bath and H. But if the bath is ideal, which means that it is very large, then the correlations are going to get dissipated, and the total amount of correlation, that total amount of entanglement, if you will, is going to be conserved, but it's going to be distributed in such a fashion that we will never be able to use it or see the effect of that again in any operation that we do in the future. This is another way of saying that a bath is a system that obeys Jane's principles, in the sense that whatever correlations you put into the bath, you assume that they are dissipated and lost. The bath is large enough and complicated enough that you will never have access to that. So you maximize the entropy of the bath at all times. Does this make sense?
Yes, that makes a lot of sense. Thanks for answering the question.
Thanks for the question. Okay, so right. So what is the end result of these two steps? I wrote step 1 there, and I should say this is step 2. So the end result is that we have ended up with C and H back in its original states. They started in tau cold, tensor tau hot. Step 1 was to swap them, but step 2 was to reset them back to the temperatures or original temperatures. But the baths have changed not in the sense that the temperatures have changed, but heat has flowed from the hot bath into the system and out of the system into the cold bath. So we've constructed a cycle whose net result is just the heat flow from the hotter temperature to the colder temperature. Okay, so now what we're going to do is we're going to turn this autonomous. So we turn it autonomous. And the manner that we do it is in 2 steps. So the swap becomes a Hamiltonian. And this is very easy to do. We take the swap unitary and we just replace the swap unitary by its generating Hamiltonian. So U being 1, 0, 1, 1, 0, 1, you can replace with this Hamiltonian H, which is 0, 0, 1, 1, 0, 0. So H is equal to 0, 1, 1, 0, cold, hot, plus 1, 0, 0, 1. One important thing to remember is that when you change from the unitary to the Hamiltonian for these swaps, they look very similar in the subspace. It's just the X, the Pauli X operator somehow. This is like a sigma X operator in that subspace, but the other diagonal elements for the unitary is 1 and for the Hamiltonian is 0. And this is important because sometimes it's very easy to make a mistake by switching and using the opposite. Okay, so rather than so what we've done now is instead of doing U rho U dagger, we've replaced this by d rho over dt is equal to minus I h comma rho. This is, by the way, it's the equivalent of the Schrodinger equation, but for d psi by dt is minus I h psi. I hope I get the minus and plus right. But anyway, this is just the equivalent of Schrodinger evolution, but for density matrices instead of vectors. Okay, so that is for the swap. And for the thermalization, I go from complete thermalization, which is the map that I showed, to probabilistic, that is a long sentence, probabilistic thermalization. And what this means is the following. So rather than rho going to tau, what I do instead is I go rho in a small time dt. There is a rate gamma, and this is the rate of thermalization. So gamma times dt, with this probability, it becomes tau. But with the probability 1 minus that, it stays as rho. So this is essentially to say, in a small time dt, there is a probability that the state rho will be reset into the thermal state. So this is aptly called the reset equation. And if I now just do a little bit of algebra, I take rho after dt minus the original rho divided by dt to get the differential equation. What I end up with d rho by dt is equal to gamma times tau minus rho. So it's essentially the rate of change of the density matrix is proportional to how far you are from the thermal state. And this, if you solve this on its own, if this is the only dynamics that is going on, it's quite easy to see that rho as a function of t, it's just a decay to the thermal state. So you get it equal to tau plus e to the minus gamma t times rho at time 0 minus tau. So at time t is equal to 0, you just get rho of 0. But as t goes to infinity, you're left with just tau. So it decays to the thermal state. What this also means is that each of the elements individually in the density matrix, they are all going to decay into the the sort of asymptotic, the steady state values that they would have in the thermal state. Okay, so in other words, so what we have now, so instead of doing U1, U2, U1, U2 on rho dagger, this was the discrete picture. What we now have is a continuous equation, d rho by dt is equal to minus I h comma rho plus these reset master equations. So plus, I'm going to call this dc on rho plus dh on rho. And dc and dh are, they are the thermalization induced by the cold bath and the hot bath. So remember that in the case of a single system, rho would go to tau. But if I was looking at one system within a larger system, then I would take rho goes to trace over C rho tensor tau C. If I was just thermalizing just tau, just C. So the same way, this dissipator, for example, dc on rho is the following. It's gamma times tau C tensor trace over C rho minus rho. That's not right. So it's the same principle as before. I take the state rho, and in every unit time dt, there's a probability that just the C part of it gets replaced by the thermal state of C. And the same way dh on rho is equal to gamma tau h tensor trace over h of rho minus rho. All right, so this is what a master equation. I don't know why the master is used for this actually, but it'd be interesting to know. But yeah, that's what's called a master equation for this scenario. Okay. And we can do two things with the master equation. We could, if we like, solve for rho of t. But in fact, there's something much easier that we can do, because when we have dissipative dynamics, what we can expect a lot of the time is that the system rho tends towards a particular state and stays there. So there exists some state that it moves towards in the asymptotic limit of t going to infinity. So what we can do is to solve, in this case, for the steady state, which is the limit t going to infinity of rho of t. And the easiest way to solve for the steady state is to just solve for d rho over dt be equal to 0. So this, of course, gives you fixed points in the dynamics. This gives you states such that if you are in that state, then you would not change. You would remain in that state forever. And if your dynamics has the two properties, one, that there is a unique fixed point, and two, that the distance to that always decreases, then what you get is that the steady state is the fixed point. And all of the thermal machines we will consider have these two properties, that if there is a unique fixed point, so if you solve for d rho by dt is equal to 0, you get a single solution. And they also have the properties that the distance to this always decreases. So remember, this is not true, for example, for dynamics that are completely unitary. So if I have just, for instance, the Hamiltonian acting, and I remove these dissipative dynamics, then I would get a density matrix rho that kept rotating in the subspace that this Hamiltonian acts on, and it would never settle on a particular state. It would just keep changing in time. It would be a oscillating state. But because of these dissipative dynamics that tend to take you in a particular direction, you end up moving towards a steady state. Okay, so and now the reason that I've introduced the concept of turning this continuous by starting from the discrete picture and then writing the continuous equation is that most of the time, and in fact, in all of the cases that we will look at, we can understand what the steady state in the continuous case is going to look like just by understanding what the static picture was. So in the static picture, we had a cold qubit thermalizing with a cold bath, which in turn was interacting with another qubit that was thermalizing with a hot bath. So if I just asked you classically, what would you expect? Well, what you would say is that we would expect that the temperature here, and this is where I should have used different notation for cold and hot. But let's call this. So in this case, now I'm going to switch notation. I'm going to call this A and B. We would expect that if we allow this to run for a while and found that it was in a steady state, we would have that beta cold, which is the coldest temperature around, would be greater than beta A, which would be greater than beta B, which would be greater than beta hot. And this is just the intuition that if I have a cold bath on one side and a hot bath on the other side and a connecting systems between them, then the temperature of all of the intermediate systems is in between them. It forms sort of a monotonically ordered chain of temperatures. And this is in fact exactly what we find in the steady state rho, which I can call rho infinity to denote that it's the state that you reach at t is equal to infinity. So our initial state is tau cold tensor tau hot, which is equal to, we can write this as R cold, R hot. So what I'm doing is I'm writing the ground state population as R. So this is the state 0, 0, and then we have 0, 1, 1, 0, 1, 1. So this R cold, R hot. This is, so to make it even simpler, I'll make 1 minus RC, I'll write it as RC bar. So this is going to be RC RH bar, RC bar RH, and RC bar RH bar. This is the initial state. And what the interaction Hamiltonian does is it rotates in the subspace. So in the end, the steady state reflects that by having some amount of population, or not population rather, but some amount of coherence in this subspace. So I'm just going to write this as some IA and minus IA. So there's some amount of non-zero coherence in the steady state because of the influence of that interaction Hamiltonian. And the other thing that the Hamiltonian does is it moves population, it slightly heats up the cold qubit and slightly cools down the hot qubit. So in the initial state, RC RH bar is greater than RC bar RH. And the reason for this is because RC is the ground state population of the cold qubit. So we have that RC is greater than RH and RC bar is less than RH bar. So that from these, it follows that this satisfied. So this is the larger population, but because of the interaction Hamiltonian, the population slightly moves in to the other level. So this gets adjusted with a minus B, let's say, and this gets adjusted with a plus B. In addition, there might be other, in fact, this is not entirely true because these populations will also change a bit in order to adjust for the population in the center. But this is something we will not go into detail now as to what exactly these values are. In fact, you will learn a very nice manner of solving for the steady state in a tutorial question. All that's important is to say the steady state of the system, it has only one pair of off-diagonal elements corresponding to the interaction Hamiltonian, and the other elements have been shifted because of the balancing between the interaction Hamiltonian trying to bring the temperatures together and the thermalization trying to reset and keep the qubits at the temperatures of their local baths. Okay, are there any questions so far? None? All right. So now one important thing to say is that in the steady state, is not a state in which nothing is happening. So the steady state is one that is formed by the balance between the interaction Hamiltonian and the two thermalizations. So the state of the system looks like it's not changing in time, but the reason for that is because the baths are exchanging energy with the system in order to balance each other out. So what you have in the steady state is that QC, which is sort of the rate of change of energy of the cold bath, is not equal to 0, and the same thing for QH is not equal to 0. Now, in the case of the discrete steps, we could calculate QC and QH by just doing a unitary operation and seeing what happens. In the case of the continuous mass equation, when I have d rho over dt is minus I h int comma rho plus dc rho plus dh rho. So I could also write this as d rho is equal to this times dt. And the energy that is poured in from the cold bath comes from this. So this part is induced by QC. So what I can say is that the heat that is put into the cold bath is given by trace of H, and this is now H naught, which is HC plus HH. These are the qubit Hamiltonians of cold and the qubit Hamiltonian of hot. H naught times dc of rho. And the same, this is equal to QC, and this, and the same way I get trace of H naught times dH of rho will give me QH. And incidentally, if I look at the rate of change of the entire system, which would be trace of H naught d rho, so all of that, this of course is 0 if we are in the steady state, because d rho is itself 0. And if I look at these, this is composed of 3 things. So one is trace of H naught times H int comma rho. But this is 0, and the reason is that H naught commutes with H int. So remember, we chose the H int, the interaction Hamiltonian, which is this one that swaps between 0 and 1 of the 2 qubits. We chose it to be energy preserving by constructing the qubits to have the same energy gap. This means that this Hamiltonian commutes with the individual Hamiltonians, well, with the sum of the individual energies of the qubits. So that is 0. And so the other 2 contributions, of course, are this contribution and that contribution, which results in the statement QC plus QH is equal to 0. Now here QC and QH both have the same sign in the sense that both of them are either into the bath or out of the bath. So all of this is to simply say that if the system has reached a steady state, then of course its own energy, average energy, is not changing in time, but that does not mean that no heat is flowing. That simply means that whatever heat is flowing in is also flowing out. So whatever heat is flowing in from the hot bath is also flowing out into the cold bath. So the steady state of this thermal machine, if you like, is one in which there is a constant rate of heat flowing from the hot bath to the cold bath, with the system remaining the same. Is there any question? None? Okay. So let's see, have I written everything? Sequence of temperatures. Right. So the final thing to say is that this steady state has correlation. So this is definitely correlated in the sense that it's not a product state. It's not even a separable, it's not necessarily a separable state because you have this off-diagonal term. In fact, if this off-diagonal term is large enough compared to the diagonal terms, and there is a formula to check for this, which you will also do in a tutorial question, you can have that this is an entangled state. And what this means is that we have constructed a thermal machine here, an isolated system, which runs on its own, whose steady state could be an entangled state of 2 qubits. So this leads to the concept of the autonomous generation of entanglement. And this is something that has been looked into quite a bit more in the last, I would say, 7 or 8 years, but especially in the last 5 or 6 years or so. And people have looked at different thermal machines and the amount of entanglement that they can generate in the steady state once you let the machine run. You can also look, incidentally, at the opposite question. You can look at the correlation and entanglement that exists in thermal machines and ask how useful it is for the operation of the thermal machine itself. So you can go from thermodynamics to entanglement, or vice versa, from entanglement to thermodynamics, to see the connection between these two. Right. Okay. So with that example, let's sort of review the properties of what we call an autonomous thermal machine. And so the first important property is that it is a closed system, which means that all of the dynamics are time independent. So you see in the example above, all of the terms that we have, h int was not a function of t, this dissipator on rho was not a function of t, and the dissipator, well, both the thermal dissipators were not functions of t. So it's a time independent interaction, which means that we are not, once we switch this on, once we construct the machine, we no longer need to interfere with it to make it do anything. And the second, to say that it's isolated, is that all interactions are energy preserving. So in our example here, we have, of course, in principle, we have 3 interactions. We have h int. We also have the interactions that made these terms happen. So they were interactions between qubit C and its bath, qubit H and its own bath. And we implicitly assume that whatever the interaction with the bath is, it is one that is energy preserving. This is actually not so much as an assumption as much as just a fact of physics that all such interactions are energy preserving, because total energy is conserved. But it's very important that the interaction Hamiltonian that we constructed was energy preserving. The reason that this is important is if this was not true, if we had that h naught comma h int was not equal to 0, then this would imply that that term here, the trace of h naught times h int comma rho, was not equal to 0, which means that even in the steady state, it would not be the case that the sum of the heat flows adds up to 0. It would add up to some number that's not equal to 0. What this implies essentially is that we would be providing or taking away in some fashion, we would be exchanging energy with this autonomous machine, or with this machine as it's running indefinitely. So the machine no longer becomes autonomous, because that means that there's an external source of energy that is continuously exchanging energy with it. So the 2 properties that we have for autonomous thermal machine are time independent dynamics, and all of the interactions are energy preserving. All right. One of the consequences of this is something which I sort of implicitly did already, is that we can work in the interaction picture. So I don't know how many of you are familiar with this, but for our purposes, it's a very simple concept. So what we have in all of these cases is we have an h naught, let's say, and an h int. So we separate between h naught, which are the Hamiltonians that exist of the systems on their own, regardless of the thermal machine, and h int, which are the Hamiltonians that we switch on upon the machine. And if I was to just write the evolution of Schrodinger's equation infinitesimally for different times and see what the state becomes, this is now more general than thermal machines. What I would get is that psi at, let's say, n times delta t, where delta t is a small amount of time, would be psi initially, and then I would have e to the minus I delta T H naught plus H int. And again, e to the minus I delta T H naught plus H int, dot, 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 say n times. So this is how you evolve. This is just a consequence of Schrodinger's equation. You evolve it for an infinitesimal time dt, and then you keep doing this. So keep continuing with this in this direction. Now, because H naught and H int, or rather when H naught and H int equal to 0, what we can write this as is we can now separate all of the H naughts and H ints, because when we have a comma b equals 0, this implies that e to the a plus b is equal to e to the a, e to the b is equal to e to the b, e to the a. We can just switch it around as we like. So all of this now becomes e to the minus I n delta t H naught, e to the minus I n delta t H int, acting on psi. So in other words, when we have that all of our interactions commute with the sort of natural local existing Hamiltonians of the system, we can separate the dynamics by saying, well, let's just look at what happens due to the interaction. And then if we want to see what the full density matrix looks like, then we just evolve it according to its natural Hamiltonian. And the reason this is useful is because the density matrix, the basis of the density matrix that we usually look at the system is the density matrix of the local Hamiltonians. So for instance, in this case here, I was looking at the density matrix with respect to the local energy Hamiltonians. And if we know what the evolution of the density matrix in that basis is, it does nothing to the diagonal elements, and it just adds off diagonal elements of the form e to the minus I em minus en times t. This is how an off diagonal term changes, and a diagonal term doesn't change because their em and en are the same, so it just becomes 0. Which basically means that once we have the evolution just from the interaction Hamiltonians, then the density matrix, the real density matrix due to the full Hamiltonian, it has exactly the same magnitude of elements everywhere. The only thing that changes is that we just have to add fewer phases at different places depending on what the energy levels are. And so what this means is that for most of our, well, for all of the autonomous thermal machines that satisfy these two properties, we can simply just work only with the interaction Hamiltonians and not have to also write down the evolution due to the local Hamiltonians always. And this is the reason why, in this case, I should have actually, in addition to H int, I should have also had minus I H naught comma rho. I just didn't write it, I sort of ignored it. And the reason was essentially this, that we work in the interaction picture, we sort of ignore the effect of H naught because we know that we can just add it as a phase to the final density matrix if we like. All right, are there any questions? Nope. Okay, so what's the time? 16:34, right. So what we have now, or what we've done, is we've sort of made up an algorithm as to how to construct any autonomous thermal machine. We simply design a static picture of what we would like to happen, and then we can turn it into a continuous machine by turning our unitaries into Hamiltonians and thermalizations into sort of continuous thermalization. So what we're going to do now is we're going to do this for the 3-qubit fridge. Okay, so what is our scenario? We have a system, we call it C, once again, and it's coupled to some bath at temperature beta C. And what we would like, this is a refrigerator. So what we would like is we would like to draw energy from the cold bath. So we assume, first of all, that beta C is greater than beta R. So this is a temperature that is colder than our room temperature, the temperature that we have, say, given to us for free, the environment temperature. So it's not so trivial to draw energy from that, because if we connected the room temperature to the cold temperature, we would expect heat to flow into the cold bath. And what we want to do is the opposite right now. So by our construction above, we know what we should do. We should couple this to a qubit, let's call this V, such that beta V is even greater than beta C. So we need to construct it to some qubit that is maintained at a temperature that is even colder than C. But of course, if we don't actually have a bath that is colder than C, we can't make this qubit by just connecting it to a path. We have to generate it somehow. And this is the reason we did all of that work on virtual qubits. We know how to generate such a qubit. So this, if this is EC, then this of course is also EC. What we're going to do is we're going to generate this in the following manner. We have and this is connected to. So we have one qubit with a large energy gap. Let's call this ER, that is connected to our room temperature. And we have another qubit with an energy gap that is exactly, it's E hot, but we choose it to be ER minus EC. And that's connected to a hot temperature. Why did we do this? We did this because the result of this is to give us the joint state. And this is just back to our virtual qubits discussion. In the joint state of these two qubits, the room qubit and the hot qubit. So in all of the discussions from now, C refers to cold, R is room, H is hot. In the joint state of the room and the hot, we can focus on the 0, 1, 1, 0 subspace. And these are all cold, hot, cold, hot, cold, cold, hot, cold, hot on this subspace. And this energy gap is going to be exactly ER minus E hot, which by construction is equal to EC. So it's a virtual qubit that has the same gap as EC, original qubit that we wish to use as a cooling qubit. And its virtual temperature, beta V, is equal to beta room E room minus beta hot E hot upon E room minus E hot. Okay, I'm not going to go through this calculation again because this is something that we did in the lecture on virtual qubits and the generation of virtual temperatures. Which another way of writing this is as, because we know that E room minus E hot is E cold, this is beta room E room by E cold minus beta hot, and this is going to be E room minus E cold upon E cold. Okay, so an easy way to write this is to say beta V minus beta room is equal to beta room minus beta hot times ER by EC minus 1. So I've just done I just subtracted beta room from both sides. And we know that beta room is greater than beta hot by construction because the room temperature is colder than the hot temperature. And by construction, we choose ER to be larger than EC, which means that this is positive. So this is greater than 0, which implies that beta V is greater than beta R. So just by construction, we have made a virtual qubit that is colder than the temperature of than the room temperature, essentially. Now, of course, this does not mean that it's colder than beta cold. We need it to be colder than beta cold, and we have to choose ER basically to be large enough. So in this expression, by increasing ER, I can make this term as large as I like, which in turn makes this whole thing as large as I like, which in turn will make beta V as close to a positive infinity as I would like. So I can generate any temperature all the way from beta room down to absolute 0, if I'm talking about T instead of beta, by just tuning the value of ER. Okay, so what I've done now is I've constructed a virtual qubit that has the properties that I want. And now I do the same thing that I did before. I write down an interaction Hamiltonian. And so my interaction is between 0 and 1 of C and 0, 1, 1, 0 of R and H. Oh, I'm sorry. Here I wrote CH everywhere, but what I meant was RH, 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 and RH. Yeah. So it's yeah, so it's this interaction Hamiltonian that I want now, and vice versa. which is very simple. So H int is equal to 1, 0, 1, 0, 1, 0 plus the Hermitian conjugate, 0, 1, 0 plus 1, 0, 1. Okay, and then of course, and then I have still my DC on rho, which is the same. I can write it as some gamma C. So this is sort of the rate of thermalization times trace over C rho tensor tau C minus rho. And similarly for R, well, for R and for H. Okay, so my final interaction Hamiltonian d rho by dt, as usual, is equal to minus I H int rho plus sum over C, well, X is equal to C, R, and H of dx of rho. And the way of writing this as a thermal machine would be something like this. This and this. This is with beta hot. This is with beta room. And this is with beta cold. And the interaction Hamiltonian is one that takes energy from the cold to the from the cold and the hot and puts it into the room temperature, or the opposite. Okay. Any questions? All right. So one thing to emphasize is that the reason, once again, the reason that we chose the combination of the room and the hot qubits to have this condition that E hot is equal to ER minus EC is to ensure that these two states, the 101 state and the 010 state, had the same energy. Because if this was not the case, then this interaction Hamiltonian would not be energy preserving, and that would not be an autonomous machine, as we discussed already. So by construction now, this is an autonomous thermal machine. And as we did in the previous case, we would expect that this works as a refrigerator if it is the case that the virtual temperature that we have constructed, this beta virtual, is actually less, is colder, so it's greater than beta cold. So if beta virtual is greater than beta cold, then we expect this qubit on the right to be colder than the qubit on the left, which would induce heat to flow from the left to the right, and then in turn from the cold bath into its cold qubit, and so on and so forth. Okay, and this is something that is borne out by what we see. So if we calculate the steady state, which of course I'm not going to do in detail, but if we calculate the steady state, we see that if beta virtual is greater than beta cold, then we have that Q cold sort of out. So the heat, if I write Q cold as the heat drawn from the cold bath, is greater than 0. And if we actually look at the steady state, it's kind of simple to see. Now we have this is now a 8 by 8 density matrix because we have 3 qubits. And what we find in the steady state is that there is only one pair of off-diagonal elements, and they correspond to the density matrix element 1, 0, 1, 0, 1, 0, and of course the opposite 1, 0, 1, 0, 1, 0. And this is precisely because the interaction Hamiltonian only works in these two states. Other than that, all of course, we have all of the diagonal state populations, X, 7, and 8. And they move around a little bit as a balance between the interaction Hamiltonian trying to move populations and the thermalizations trying to reset. So what we find in the steady state, so imagine our initial state is tau cold tensor tau room tensor tau hot. So it's just the thermal states of each qubit at its own temperature. Then this goes to a rho infinity, which has the following property. So I can always take rho C to be equal to trace of, so this is out of the steady state, trace over R and H of rho infinity. And similarly for R and H. So I take the steady state and I look at what the steady reduced state of the C qubit is, the R qubit is, and the H qubit is. And what I see, if cooling is working, if the construction was that beta virtual was greater than beta C, what we see is that rho C is colder than beta C. So rho C infinity, let's call it. Rho R infinity is hotter than beta R, and rho H infinity is colder than beta hot. And what this means is that, so this will imply that QC out is greater than 0, because the qubit rho C that is attached to the bath C is colder than the bath, so it will accept energy from the bath. The same way QH out is greater than 0, but QR out is less than 0. So QR in is greater than 0. So this is a machine that, exactly as you expect a fridge to work, it takes heat from the cold bath and the hot bath and puts it into the room temperature bath. Is there any question so far? Nope. Okay. Yes. So now there's one important thing to say. So this rho infinity that we have, we can actually write it as tau C tensor tau R tensor tau H plus some sort of, let's say, delta rho. And this delta rho is proportional to the bias. And what this bias is equal to the population of 0, 1, 0, that's 1, 0, minus P of 1, 0, 1. So what this means is the following. When I take my initial state, tau cold tensor tau room tensor tau hot, I'm going to have these two energy levels, 0, 1, 0 and 1, 0, 1. My interaction Hamiltonian simply rotates in the subspace, and that effect is symmetric because it rotates back and forth. But because this started out in this product of thermal states, these populations are not the same, which means whichever greater population is, there's going to be more flowing from that to the other state than vice versa. So what we get is that the rate at which heat flows in the steady state is proportional to how asymmetric this bias is. And this bias, incidentally, is actually proportional, is related to beta V minus beta C. And the way to see it is the following. So P0, 1, 0, and this is in the initial state, is equal to, so it's P0 cold times P1 room times P0 hot, because in the initial state, you just have a product of thermal states, so it's just the product of the individual populations. And this is equal to, so this is ER beta R upon Z. This is just 1 plus e to the minus beta. So this is just the partition function for each of them. Z cold, Z room, Z hot. And P101 is equal to P1 cold, P0 room, P1 hot, which is equal to, now you have excited in the cold and the hot. So this is e to the minus E cold, beta cold, e to the minus E hot, beta hot, upon the same thing, Z cold, Z room, Z hot. And therefore, this bias is equal to e to the minus ER beta R minus e to the minus EC beta C, E hot beta hot, upon the Z CRH. I'm just going to combine them all together. And if I take e to the minus ER beta R outside, ZCRH, this is 1 minus e to the minus EC beta C times E, well, actually, no, let me do it the other way. Sorry. e to the minus e hot beta hot. And this is now e to the minus er beta r plus e hot beta hot. And this is minus e to the minus ec beta c. And this thing is equal to e to the minus beta virtual ec minus e to the minus ec beta c. So this is greater than 0 if and only if e to the minus beta vec is greater than e to the minus ec beta c. Oh, no, yeah, indeed, which implies that I need that beta v is less than beta c. So in fact, I should have started the other way. So I should have called the bias to be the negative of this so that we get that beta v is greater than beta c. So anyway, so this is now proportional to negative of the bias. So negative of the bias is greater than 0 if beta v is less than 0. So the bias is greater than 0 if and only if beta v is greater than beta c. Okay, so all of this is to say that the steady state, the difference of the steady state from just the product of the thermal states is proportional to a number that essentially encodes how much colder the virtual temperature of the qubit that we constructed is than the temperature that we are trying to cool, the temperature of the bath that we're trying to cool. All right, this was a slightly hand waving because I didn't write actually the full density matrix. Is there any question on this? Was this clear? All right. Okay, so the final thing to consider for this scenario is let's talk about the efficiency. Now, what is the efficiency of a fridge? So the useful heat is QC out, which is the heat that we draw from the bath that we're trying to cool. And the resource that we have is QH out, which is the heat that we draw from the hot bath in order to power the refrigerator. So this, yes, we will be doing a short break. What I will do I'll do this immediately after the after this talk about the efficiency. Then we will do a short break because at the moment it's would be a bit unnatural. Right. So QC and Q hot are the useful thing and the resource. So the efficiency is just defined as the ratio between these two, QC over QH. But because the only manner in which population can move in this machine is via this interaction Hamiltonian, it means that whatever population goes down in cold is exactly the same that goes down in hot, and it's exactly the same that goes up in the room temperature. So whatever population change we see on cold is exactly the same population that we see on hot, and it's negative of the population that we see on the room temperature. But this is, of course, a population. The heat is the population multiplied by the energy, which means that QC over QH is exactly equal to EC over EH. So without actually having to calculate what the exact heat is, we already know that the ratio of heats is going to be the ratio of energies. And so now I want to find what is the maximum of eta of this efficiency. And the way to do this is very simple. As long as this machine is working as a refrigerator, we know that beta virtual must be greater than beta cold, which is to say, and beta virtual, remember, was beta room E room minus beta hot E hot, which is E room minus E cold upon E cold, should be greater than beta cold. Sorry. And now we can convert each of these into eta because we know that, so eta is equal to EC over EH, which is the same as EC over ER minus EC. So, which is also the same as 1 upon ER upon EC minus 1. So this is also the same as saying that ER over EC is equal to 1 upon eta plus 1. So we can convert freely between the ratio of energies and eta. So this then becomes beta r times 1 upon eta plus 1 minus beta hot times exactly 1 upon eta is greater than beta cold. And this, after little algebra, you get that eta must be less than beta room minus beta hot upon beta cold minus beta room, which if you write it in terms of temperatures is this. And the only reason I'm writing it in this form is because this is the form that if you just Googled what is the Carnot efficiency of a refrigerator, you would get exactly this expression. And so we find that this really matches with our understanding of the Carnot machine in the sense that we have an efficiency that is the ratio of energies. And as long as the machine is working as a refrigerator, then it must mean that the ratio of energies is bound by this value that gives us that the maximum efficiency that we can get for the refrigerator is the Carnot efficiency that we know from classical thermodynamics. Okay, are there any questions at this point? Nope. All right, so then let's take a short break and we can return at, let's say 5 minutes past 5. So in 7 minutes from now. See you then. Very good. Right, so what we've done essentially is followed a template that we can now repeat in various ways. So one of the first things to do is to go from a fridge to the opposite. So in a fridge, we try to make a temperature that is colder than the room and the hot temperatures, which are the ones we have access to. And we do that by taking a large energy gap, connecting it to the room temperature, smaller energy gap connecting to the hot, such that the difference is equal to the energy of the system that we are cooling. If we switch the temperatures that were connected to these two energies, so we connected the larger one to hot and the smaller one to the room temperature, then we would end up generating a beta V that was given by this formula instead. It's the same as before, but it's just now the switched roles. I've called this EW instead of EC, not because it's a different type of system, but just to say that it's now fulfilling a different role. It's something that is where population is being driven upwards rather than downwards. And there you can see that you end up with a beta virtual that is actually less than beta hot, which is the same as saying TV is actually even greater than T hot, if positive. So this is an engine or a heat pump. Now, heat pump is just to say that you push population higher than it would be at the normal temperature. But in order to have it be an engine, you have to have something even stronger. You must have that there is a greater chance of the population to be in an excited state than in the ground state. And for that to happen, you must have that. So for an engine, beta V must be less than 0. So you have a negative virtual temperature so that e to the minus beta V times the energy is actually greater than 1. So the ratio of the excited to the ground state population is therefore greater than 1. Now, if you were to connect this to a qubit like we had before, then you would just end up creating a qubit with an inversion or a sort of greater population in the excited state. But you could make something that looks really like in the classical version of an engine by connecting this not to a qubit, but instead to a ladder. So you have every thing in the ladder is EW, every gap, energy gap in the ladder is EW, which is of course equal to E hot minus E room. And this is so that the interaction that we're about to write down, as usual, is going to be energy preserving. And so what you have then is that the interaction Hamiltonian is equal to 0, 1, 1, 0 on the hot and the room qubits, tensored. Now, if I go from 0, 1 hot, which now the hot qubit has a higher energy gap, so this is excited on the hot, to 0, 1 on where the room is excited, this is a decrease in energy. So this is now going to be a lowering operator on the ladder, which I call W, plus the Hermitian conjugate, which is 1, 0, 0, 1 on, hot and room, tensor the lowering operator on the ladder. So this is now a new interaction Hamiltonian. And in this case, the hot in the room, they are still the hot, the dissipator, the thermal dissipators on the hot, the thermal dissipator from the room, but there is no dissipator on the ladder. The ladder is just as it is. So imagine that I constructed now a continuous, an autonomous thermal machine that had these things. So it had the interaction Hamiltonian constructed as follows, and the thermal dissipators on the hot in the room. We're not going to get a steady state. So if the ladder, I assume here the ladder is unbounded. So we're never going to hit the edge of the ladder on one end or the other end. So it's unbounded. Then what this is going to do is in every unit of time, there's going to be some probability of moving up on the ladder because of this interaction Hamiltonian and some probability of moving down on the ladder. By construction, if I make it so that the virtual temperature from the room and the hot qubits is negative, then the probability of moving up on the ladder is going to be higher than the probability of moving downward on the ladder. So what I'm going to get is something that looks similar, but it's not exactly the same as a biased random walk on the ladder. It's not exactly the same because the joint state of all of these three systems is not classical. It's not diagonal. You're going to have some off-diagonal terms, just like before because of the interaction Hamiltonian. But they are going to be small compared to the actual movement of the diagonal elements on the ladder. So what you get is, instead of a steady state, you get asymptotic rates of dEW by dt. So you can sort of calculate in the long time limit what the rate of change of average energy of the ladder is, and also of d of sigma squared by dt. So this is just the spread of the energy of the ladder. So you calculate the first movement of the ladder, you calculate the movement of the second moment of energy of the ladder, and then from that you can calculate the movement of the spread. Because it's, as I said, it's like a biased random walk. It not only moves up and down, but there's a probability of moving up and a probability of moving down. So you also have that it spreads as it moves. But like in the case of a biased random walk, the movement of the first moment is of the order of t, whereas the movement of sigma squared is of the, well, not of sigma squared, but of sigma, the variance of the not this variance, the standard deviation of the energy of the ladder, that spreads as square root of t. So E average goes as t, and delta E average goes as square root of t. So you do get that this looks like engine, because the signal to noise ratio of how much energy you've put in to the engine is, or to the ladder in this case, is something that goes itself as square root of t, which is an increasing function of time. Now, the interesting part is to see what happens when beta v is equal to 0. Then there you get equally biased. And in this case, what you find when beta v is equal to 0 and you're equally biased is that, well, E average doesn't change because you have equal chance of going up or down, but you still spread because you have a property of moving up and down, which means that there you don't actually do any work, but you end up spreading the ladder. And this, in fact, can be seen as the Carnot limit of the engine. So in the same fashion that we looked at the efficiency of the refrigerator, we can look at the efficiency of the engine as well, which would be the asymptotic dE average by dt divided by Q hot. So the amount of work that you put into the ladder divided by the heat that you draw from the hot bath. And if you calculate this is going to be equal to, just like in the previous case, the ratio of energies EW upon E hot. And if you do the same thing that we did before, remember that what we get is less than, and this is work because the ladder is moving downwards. You end up getting that this is equal to 1 minus beta hot by beta room, which is of course the same as 1 minus T room by T hot. And this is the Carnot efficiency of an engine. Okay, so this is really straightforward adjustment from the fridge to an engine. The only difference is that we replace the system that we're acting upon. Instead of a qubit, it's now a ladder to allow us to accept more energy than just the energy that you can store in one qubit. Okay, so from there, we can go to a lot of other examples. So and all of this is just to give you an idea of the wealth of complexity of autonomous thermal machines that one can consider. So one thing that you can do is you can do everything that we considered so far with harmonic oscillators. So for instance, in the case of the fridge, rather than have a qubit, we could have an oscillator C, an oscillator R, same thing, an oscillator H. All we have to do is we have to choose omega C plus omega H to be equal to omega R, where omega R, where omega are the frequencies of each oscillator. And then we can have that the interaction Hamiltonian is equal to A dagger C, A R, A dagger H plus the Hermitian conjugate. So it's the same principle as before. Raise the raising operator on C and on H, and the lowering operator on R, which means that you extract energy from C and H and you put it into R. So this is these two in combination. Well, this interaction Hamiltonian in combination with the degeneracy condition that we've just written down on the frequencies imply that the interaction is energy preserving. So then you add this plus dissipators on the oscillators with thermal baths, and you get exactly, well, not exactly the same because you're going to have a different dynamics now because you have oscillators, but you have the same effect as we had in the case of the 3-qubit fridge. You will end up extracting heat from the cold and putting it into the room. The condition for cooling is also going to be exactly the same as in the case of the qubit. You're going to have that beta virtual should be greater than beta cold, and instead of E cold, you just take E cold, room, and hot, and you replace them with W cold, room, and hot, and you get exactly the same condition for cooling as before. So you can do everything we did with qubits for harmonic oscillators, and it will work just the same. The second sort of example is with thermalization of, let's say, within systems. So in the fridge that we constructed, it was sort of the simplest possible because we really took just a qubit and a qubit, but we demanded that the part of the system, there is a separate system that was connected to the room temperature bath and a separate system that was connected to the hot temperature bath. We could, for example, do something that is a bit more fine-tuned. We could, for instance, instead of saying and this is E hot, so that this becomes EC. And then what we can do is we can thermalize this transition to beta hot and thermalize this transition to beta room. Now, I'm not going to write down the thermalization map for this, but the way it goes is very simple. You leave the population in the other energy level the same. So you don't interfere with the last energy level. You simply take the populations within the energy level that they're thermalizing, and you move them closer towards the Gibbs ratio corresponding to that temperature. So rather than thermalize the entire state of the system, you thermalize only a subspace of the system. So this, of course, practically to implement might be more difficult than constructing two different systems, each connected to its own path. But if you're allowed to do this, then you can have a different class of machine. So then in that case, the smallest possible fridge turns out not to be a 2-qubit fridge that cools a third qubit, but rather just a qubit fridge that can cool a qubit, because now this last transition is the one that you couple to your system with energy gap EC. So you could construct a whole different class of thermal machines if you're allowed to thermalize individual transitions. And the last thing that you can consider is just making more complicated of thermal machines. So for example, I can do exactly the same thing that I had before. So I have a Qubit, and this is a transition that I want to be very cold, because this is going to couple to my system that is to be cooled. And I do it by coupling this to, not E, sorry, coupling the large transition to beta room. But now, instead of coupling the top transition to a hot temperature, which is what we did in the original fridge, I'm going to actually, instead of coupling it to a hot temperature, I'm going to couple it to an engine, which is even hotter. So this is now going to be coupled to another transition. And that transition in the new Qubit is going to be an engine. So this is going to be this coupled to hot, and this coupled to the room temperature. So what it looks like, if you just look at this alone, this is a heat engine. It's a heat engine that induces the top transition to be at a temperature that is even hotter than beta hot. But that in turn is coupled to our original fridge, which ends up creating a virtual temperature on this cold transition here, which is even colder than the original fridge just on its own. And of course, I can continue this process. I can now replace, I could, if I like, take away beta room, and now instead couple this to the lowest transition in a fridge, and so on and so forth, and just extend this arbitrarily as much as I like in order to create colder and colder virtual temperatures. So this is a useful thing to consider if we are bound by the Hamiltonians. Because remember, in the original fridge, we said that we could create any temperature we like as long as we were able to increase the gap of the room Qubit as much as we like. But this is an alternative way to do the same thing. If we cannot create as large energy gaps as we like, we can still, with finite energy gap, couple many machines to each other to create colder and colder virtual temperatures. Okay, right. Is there any question so far? Any question on this part? Okay, so we have only 10 minutes left, which means that I cannot completely speak about thermalization, but I would like to introduce the topic anyway. So and that was completely fine. All we did is we just found the generating Hamiltonian, and we wrote down the Schrodinger evolution due to that, which is this d rho by dt is minus I h int by rho. And this is completely fine. But the other thing that we did is we wrote down these dissipators, which at the moment I wrote down as gamma times trace over some operator C of rho tensor tau C minus rho. And this is something that we just assumed that we could do. So we could have an interaction with a thermal path whose effect is going to be that it gives us this sort of reset, or the reset thermalization equation to us that we can put into our thermal machine. Now that actually has a lot of assumptions behind it. And I'm going to sketch somehow the process of doing this. So what we're going to do is we're going to look at the process of going from the full interaction of system and path to the Lindbladian picture. Okay. So this is in 2 steps. So the first thing we do is the following. So imagine now that I actually looked explicitly at the interaction between the system and the bath. So I have a bath. I'm going to call this bath, let's say E, so standing for the environment. This is coupled to my system S, which in turn is part of a global system. Let's call the rest of the Hilbert space S prime. So there's S and S prime, and S is coupled to the environment E. So I know that the most general map that I can write down on the system S is of the following. So rho S goes to sum over K of AK rho S AK dagger, where sum over K AK dagger AK is equal to identity on S. So this is the most general CPTP map that's completely positive and trace preserving map that we can write down on a quantum system. But now I could consider, imagine that I did this map and this map occurred across a certain amount of time. Could I sort of break down this map into the evolution of the system for various sort of infinitesimal units of time? And if I did this, what is the infinitesimal evolution going to look like? So what I can consider is, I can consider rho S and I can break it as rho S in a time dt becomes rho S of, well, rho S of t becomes rho S of t plus dt. And I ask, what is d rho S, which is equal to, well, rho S of t plus dt minus rho S of t. Now, this is something that will be essentially the second tutorial question that you have this week. You can calculate this, and what it turns out to be is that ds of rho always can be written in this form, minus I for some Hamiltonian commuting with rho, plus the sum over, let's say, j of these operators, Lj rho, Lj dagger, minus half the anti-commutator, Lj dagger, Lj with rho. So this is a very powerful statement, and it says the following. If I take a quantum map and I look at the infinitesimal change in the state rho, so essentially what I do is I take this map, if this is d rho s by dt, then this is to say that if I take the integral of this ds rho s by dt times dt, I will end up getting rho s of t minus rho s of 0. So by doing this, I can get back the original map. And the statement, the Limbladian sort of theorem, is to say that any general map, the infinitesimal dynamics of the map look always like they have this form. You can always write it as the infinitesimal change is due to some commutator of a Hermitian matrix. So this H is Hermitian, plus a sum over these Limbladian operators. And these L's are arbitrary. So they need not be Hermitian or anything. They're just arbitrary operators on the Hilbert space of S. Okay. However, if I was to do this for a general map, what I would find is that I could split the map into small infinitesimal components. Each of them is going to be described by Limbladian, but the Limbladian for each component is going to be different from the other ones. So these Limbladians are all going to be, in principle, functions of t. So that when I put them inside this integral here, the integral is not just going to be just a straightforward sum of the same operator acting on the system repeatedly. No, that operator is going to change. And the reason for this is quite simple. It's because some dynamics between the system and the environment are going to induce correlations between the system and environment. And as those correlations are being induced in the system and environment, and as the environment on its own changes due to its own Hamiltonian, the effective action of the environment on the system is also going to change in time. So in general, the Limbladian itself is a function of time. So if I call all of this the Limbladian on rho, so this is just a Limbladian operator. This is in general going to be a function of time acting on the state rho. Okay, however, there are ways to simplify the Limbladian and this is essentially the process that takes the most general map that we can consider into the Limbladian that we expect to get by interaction with a thermal bath. And there are a number of assumptions, and the assumptions are the following. So this is again something I will not go into the details of how each assumption then simplifies the equation, but this full derivation is to be found in a textbook by Petruccione and Breuer. It's called Open Quantum Systems, and it does it in very nice detail and very pedagogically. So you can follow that if you would like to see this in greater detail. But there are a number of assumptions. One is that the correlations between the system and the bath and within the bath are lost quickly. So the time scale over which these correlations disappear because of the bath being complex, like we don't know the reasoning behind it, but except that the bath is complicated enough that these correlations spread out so that they are lost. That time scale is very short. It's also the assumption of, there is also this assumption of Markovianity, which means that any correlations between the system and bath correlations do not sort of return, in the sense that whatever correlations you build between the system and bath, they are lost quickly enough that they do not come back to affect the dynamics at a later time. So these, of course, the two things that I've written down are not completely independent. And the third thing is that the bath itself is ideal. So it's large enough such that whatever quantities you exchange with it doesn't actually change its state. So its temperature, for example, remains the same, etc., and all of these other properties. When you have a bath, that an environment or a bath that is large enough that it satisfies these properties, the correlation timescale, Markovianity, it being ideal, then what you end up with is a Lambdadian that is independent of time. And that's good because then you can just write d rho over dt is L of rho. And that also means that rho of t is actually just e to the minus L times t acting on the state rho. Because you can integrate this, you don't have to worry about the different L's at the Lambdadians at different times commuting or not commuting. You can write this expression because it's a time independent Lambdadian. In addition, we have two more assumptions. So the first is, so the interaction is energy preserving. HSB. So the interaction between the system and bath, or SHSE, if it was labeled by E, is energy preserving. So that effectively means that the interaction is of the form, if energy is gained by the system, then it's lost in the bath and vice versa. And what this induces is that the LJ, the operators that we find in our Lambdadian up here, they are jump operators. So they are operators that essentially take us from one energy eigenstate to another energy eigenstate of the system. So for example, for a qubit you have sigma plus, which is equal to 0 going to 1, and sigma minus, which is equal to 1 going to 0. So these are jump operators that take you from one energy eigenstate to the other energy eigenstate. And the final assumption is that thermal bath, so the jump operators obey detailed balance. And what this means is that, well, one of the ways of writing this equation, I can write it as in this form, but I can also just mathematically take out a gamma j and then have the norm of each of the LJ be the same. So this gives me sort of an idea of how strong the effect of different types of jump operators are by making them the same norm and just removing the strength as a factor on the outside. And what we get for thermal baths is that these factors, they obey detailed balance, which is exactly the same as saying that they have the Gibbs ratio between them. So for example, if sigma plus and sigma minus, I have that gamma plus divided by gamma minus should be e to the minus beta times e. And this is basically to say the strength of the jump operator taking you from the ground to the excited state. So the strength of that Lambdadian divided by the strength of the Lambdadian taking you from excited to ground is exactly equal to the Gibbs ratio. And what this means is that the ratio of these two processes is going to take you towards a state which has the same Gibbs ratio. because now you can check that if your starting populations already have the Gibbs ratio, then these two Lindbladians are going to exactly balance out each other. So in summary, if you start with a bath whose correlations are lost quickly within itself and within the system, and which as a result is Markovian and is large enough so that its own properties and its own state do not change in time, you get a time-independent Lindbladian. In addition, if you have that the interaction between system and bath is energy preserving, you get that the Lindbladian is just composed of jump operators. And finally, if the bath itself is thermal, the strength of different components in the Lindbladian are going to be given by detail balance, which is essentially the Gibbs ratio of the bath. And that induces that the steady state of the bath that the Lindbladian takes you to is exactly the the steady state of the system that the Lindbladian takes you to is exactly the thermal state of the temperature of the bath. Is there any question on this? Nope. Well, then in that case, I think we can wrap up the lecture. Thanks for waiting the extra 5 minutes from my usual time. And I will see you next week to conclude a little bit of thermodynamics and immediately then go into clocks. Thank you very much. See you next week.